is a torsor over the affine lines today.
Thank you. Torsors over the affine lines today.
So A1, okay, so what I understand is that he is the main player of these 3 weeks. Okay, so remember yesterday, okay, for G over K reductive, and given here maximal torus, we have seen that over K bar, okay, so K is my field, okay. So when I have field K, I have 2 over fields, so the separable closure and the algebraic closure. We have seen that so H1 of A1 K bar T maps onto, because H1 A1 K bar G, okay? And so T is a split torus because over K bar everything is split, so that's the reason why the theorem of yesterday apply. And this thing is the same thing, that peak of A1 K bar, okay, which is this K bar T ring, R powers, this is 0, okay? So this guy is 1. Okay, so the theorem we shall call R like Raghunathan-Ramanathan. This result is exactly 40 years old, okay? It's from 1984. And we take G over K, a reductive group. So I said yesterday what I mean by that, okay? Then I'm not saying that the H1 is trivial, I'm just saying that the H1, those which are split by the separable closure, Ks, this thing is 1, okay? And of course, if K is perfect, so Ks is K bar, and if I take that, it implies what we want. Okay? So this is an homotopy result. And you might ask what happened when K is not perfect. And then that object is not already, okay, so there are examples, so I will say in small characteristic with respect to the group, okay? And so you know, for example, 2 is really special when you deal with orthogonal group, okay? Or so only for those very special prime called torsion prime by Serre, exotic things might happen. So those exotic things, the simplest one is when I take K non-perfect, so imperfect, and of course P is a characteristic, and you take an element A which is not a P power, okay, so, and you take G to be PGLP, okay, so GLP mod GM, and the projective linear group. So in that case, H1 KT of G by this yoga of form, so PGLP, you know, is a group of automorphism of the matrix algebra MP, okay, and then it corresponds to form of that, and these forms are called Azumaya algebras. Azumaya KT algebra of degree P. And so I have to to write with this A an example like that. So, and an example is of A. So you take the presentation. Xp is, sorry, xp minus s is a t, and t is my coordinate here. Yp is my A, and we have to say how y acts on x. But look, this is a Hartin-Schreier extension, so we know how acts. So this is a cyclic extension, and when the Galois group acts by like that, by x go to x plus 1, okay, and then this is a way to remember the equation. So xy minus 1 has to be x plus 1. So this thing defines a central, an Azumaya algebra, which is not 0. Okay, so A is not 1, is not trivial in H1 KT PGLP, but it's even stronger than that. Okay, it is not trivial when you go to KS, when you go to the separable closure and you invert T. And of course, as you can see, this is related with this Hartin-Schreier ring, and as you know, the affine line is not simply connected in positive characteristic. Okay, and there is a way to write this thing. Okay, if you don't like Azumaya algebra, we can write using groups. So maybe I explain how it goes. So in PGLP, you have a very nice group, which is the following. So you have mu p, okay, in GLP. Okay, what is mu p? And this is 1x xp minus 1 for x being in mu p. So you have this embedding. In the other hand, you have some ZPZ in GLP, which is just to give one matrix. So you take 0 at the diagonal, 1 here, and 0, and 1 here on the corner, and 0 otherwise. Okay, so it's a cyclic matrix. And what you see is that when you take a guy like that, they do not commute, but they almost commute. They commute up to the center. Okay, and then when you see them projectively, you get yes. No, yes. Thank you. Yes, you get a group like that, right? And I said 10 times, functoriality is the main issue. Okay, so once you have a group, okay, you can put here. You need the flat thing. You put your ring KT of mu p. Here the same with KT of ZP mod Z. I mean, you have this map I. So this map E lower star, which goes in. Also G is, as I said, G is. This is J. And here, you can apply Kummer theory. So since KT have not unit, this is K star mod P. And here, you can apply Hartin-Schreier theory. So you know, that this thing is KT modulo guys of the C shape, x minus x, okay, for x running over KT. And what I have done here, that class I wrote, okay, it's a I mean, of course, you have to work a bit to check this is true, but this is true, is that you take, in these things, you take the simplest guy you can find, you take 1 and t, A and t, and A and t gives that thing. Okay, so this thing, so. Give A by this lower star. What?
Do you have some invariant that has to
Exactly. So I'm preparing my ground. So
Tell us later on where it lands? Or?
no. Just to tell you that the problem is at infinity. Yeah.
It's not the Brouwer group, though, at infinity. It's something else. I mean, it's not the case, it's the arbitrary elements at infinity.
Exactly. But, no, but I mean, it's a good point. Because what this thing tells you is that this Azumaya algebra not only satisfies that, but there is no way to extend this as PGL torsor to extend it to P1. Yeah. Because over P1, Grothendieck tells us that indeed, if you have a torsor over P1, when you restrict it to the affine line, it has to be constant. Okay? And I will come back to that. Do not worry. But that example is important. Okay. Is quite easy to do. What is harder is to make kind of this exotic example with a semi-simple simply connected. Okay. So in the notes you have reference to how to make that. Okay. But it's okay. So we have this beautiful result. Okay. And so it was proven. So a long time ago, but people had it. I mean, if you look at the original proof, it's quite fast, I would say. So in my thesis, I did my own proof because I used that crucially. So then we did one other proof with my Canadian colleagues, Chertouzov and Piazzolla, and just 2 years ago, there was one more proof of it. So the last proof, which is a variation, of course, which is not very different, but which is simple. So this is Abramenko and the Rapinchuk. So for short, this is Rapinchuk square. Okay, Andrei and Igor. And today, I will not prove the general form. Okay. Because I will prove the first very relevant case where we use Brouillatti's theory. So let me just say that all proofs use Brouillatti's theory, and Brouillatti's theory concerns exactly this field at infinity. So before to prove the theorem, I have to tell you what I use from Brouillatti's theory. And so my field will be the field as infinity. Okay, so our plan today is to prove this theorem in the case G over K split, semi-simple, simply connected. And I mean, with the delta, with a connected. And delta is the declinogram of this group. Okay, so this is not the general case. But for example, it includes the group of type E8, okay, which is already something, okay? So for that we need Brouillatti's theory for what? For G and for the field K. And since I take this is the field as infinity. Okay, so if you don't like 1 over t, you can take t, but later it will be with t. And so Brouillatti's theory, it's a long story. Okay, so you have you have several things. I mean, you have an abstract subgroup, and so it's about this group. So this group is as you know, this is a topological group, because that thing has a valuation. So it's about certain nice bonded, maximal bonded subgroup of these things. It's about Euclidean buildings, you know, some space I will talk about. And there is one there are two other parts. Okay, one is about integral models of this group, so that will not occur today, but it occurs for example, in the original proof. Those integral models, and there is also one other part which is not so known, which is about Galois cohomological issue, and actually I will use them today. Okay, not by quoting them properly, but by redoing some argument of these Galois cohomology things. Let me tell you something. So Bruyati's theory is not easy. Is not so easy to access because you have these big volumes which are very general. So that's also the reason why I discuss that specific case. But now there is an amazing book by Kaleta and Prasad, which is really big, but you can read it. It's so fast. It's amazing. Okay, so in other words, right now there is no excuse to not be aware in Bruyati's theory. Okay, so what I need is this space. So what I will do is what everybody does when talking about Bruyati's. They take a board to put a picture with an SL2 case. So I will reserve this board for that. Okay, so the SL2 case, take G as SL2, and I take the field with two elements. And how looks this Bruyati's building? It's a tree. So you have a thing which is called the center, and then you have to think about things around the centers as it's called the link. It's a projective space in F2. So then you have three elements. Okay, so you have one thing like that, one thing like that. Okay, and then you continue, but smaller because well, actually you can go at infinity, but I'm not. Okay, and so this space is similar with the Poincaré disk. Okay, so I will come back to that. Okay, so, and as you know, you can describe the vertices in terms of lattices. Okay, so we have this K. So this K has a ring of integer of valuation, which is this thing, and so the center here, it corresponds to the obvious lattice. Okay, this is O plus O, and here, well, it's not exactly the lattice. It's a lattice up to homothétie. Okay, and here you can look at this point, which is O plus 1 over T O. Okay, and so on. Okay, so in general, so the building B of BGK, okay, is a contractible. So you can see this object is contractible, right? Simplicial space equipped with two things. Equipped with. So first, you have an action of G of K on it. Okay, so which is strongly transitive. We will come back. I will say later what I mean precisely. And secondly, it's a metric space, okay? It's a metric space with, with a with a GK invariant matrix. A metric, okay? Well, and well, so you have this huge space, and we know how it looks. So for each K torus, maximal torus, so sorry. Maximal, so K split torus, T. You have inside G, we have inside B, we have so-called the apartment. Okay? And so this apartment is really nice because it is when you look at it, is an Euclidean affine space. Okay? So so in the SL2 case, apartment are the line. Okay, so I can start with A, go like that. This is an apartment. Okay, so also I can go by there and go there. Okay, and if I take T inside G over K, okay, over the small field, so I get what I get. I call it the standard apartment. And this standard apartment goes through the center of the building. Okay, so I did not define precisely, but you can imagine there is a center in that big building too. And then, since, you know, when I have an affine space and a point, I get a vector space. So what is this vector space? This is, when I take these canonical things, these standard things, it is the center plus a vector space, which is Euclidean, which look like that. You take the co-character and you tensorize by R, okay? And then you have an action of T or capital K on that by translation, okay? So and of course, if for SL2, okay, SL2, T is just GM, okay? And then it tells you that what you have, a line is really a line. Okay. So the main input for what we do today is something proven by Christophe Soulet in 1979. So please be free to ask questions. Yeah. So Soulet investigated the action, okay, of the group G K of T on this building, on B. Okay, so because, no, sorry, J capital K. Okay, so remember K, this is this thing, and of course, it contains the polynomials, okay? And the theorem is the following. So of Soulet, right? so maybe I should before to start I need to define something. Well, so we need more notation. So I was with my standard thing, okay, and then as you know, I can define the root system. I can put an order on it. I mean, so namely to find a base, okay, base of simple roots, okay, and then he define this thing which is called is a cone, which will be phi. I mean the center of the building plus so the elements here, okay. But when you have a co-character and a character, you can make a pairing, okay. So you look at the V, which are here, such that when you look at alpha of V, okay, so this is a pairing between a character and co-character. This is, of course, this is a real number because I tensorize over A. It has to be non-negative, okay. So you can call it the Soulé's cone or whatever, and the Soulé's theorem tells you that this cone is a fundamental simplicial. So it's better maybe to permute these two words. Simplicial domain for the action of G kt on B. Okay, so what means simplicial, fundamental simplicial domain? It means you have to reason simplex by simplex. So it means any simplex of the building is equivalent to one unique simplex of the cone, right? And this contrasts with a, okay, so, and then recall what I said before, okay? So the fundamental domain for the group GK is just the adherence of a chamber. So it's much smaller. So in particular, it is bounded. So on my picture, okay, what Soulé tells you, okay, is that you have only this line here, okay? So this is Q, okay? So only this half line is a simplicial fundamental domain. And if I want just the action of J of a capital K, this is a fundamental domain. Okay, so maybe it seems to be. So why this thing is useful for torsors? So I come now to that, and I will have to say that Soulé's work is more than that. Okay, it tells you also what are the shape of the what are the shape of the stabilizer for this action. Okay, and it gives you some remark. So this thing, so remark, no, it's not good. Remark, so Soulet obtained a presentation of this group, generalizing Nagao theorem. So Nagao theorem is that picture. Sorry, Nagao's theorem. And Nagao's theorem tells you that what is the group SL2KT? This is the amalgamate product of SL2 of K over B. So here you put B K of T, so B as a group of upper diagonalized matrix, and amalgamated under the intersection, which is B of K. So that many people know because it's in Serre's book 3. So this is a generalization of this kind of things. And now, when I have Soulet theorem, I can go to the proof of Raghunathan-Ramanathan, and you will see you can really think about it as a consequence. So, okay, so now I want to keep that. Well, so I go to the proof, of course, in my specific case, right? Well, so now proof of RR. So remember, it was about a A1 torsor which trivializes over KS. Okay, so concretely, okay, so we are given. So what happened is that if you took the Galois cohomology of so KS of S of these things, okay, so this is the same thing that this kernel, okay, H1 KT G going to H1 KST G. Okay, so then a guy here is just a Galois cocycle, okay, ZS, but is not in value in GKS. We have one variable, and then the trick is to use Soulet theorem not over K but over KS. Okay, so B prime, if you want, this is the building. Well, actually, it's even better. No, we have to work at finite level. Sorry, so I go too fast. Well, so this S, okay, factorize. So there is K prime over K Galois of group, say, G gamma, such that ZS is a cocycle with this. Okay, so we can always, by limit things, work at finite level. So we will see why it's important. So I did not by B prime the building at G K prime, and K prime, of course, is. So what I'm doing now, I use the above results over this field K prime, and I will put prime everywhere to this Q prime and so on. Okay, and here and so. And then I did not say, but we have a Galois action, so of what? Of gamma on B K prime. Okay, so So the thing, if you prefer, the construction of this building is functorial in the field, okay? And then you have a Galois action, okay? So, and in terms of lattices, this is clear what I mean, okay? So in the sense that when you have a lattices, you can conjugate it by Galois, okay? And so this, and then the fact we have that, we can twist this action so that by our cocycle Z as follows. So I denote by star the new action, the twisted action. You take X, this is the point of this building B prime. And what is the twisted thing? You take the classical action, so the action you are given here, and you apply the action of the group, because again the group acts on it. Okay, so this is the sigma. And this is an action. And I have a finite, I have a finite group action on a Bruyatilis building, so something like that. But here comes the point I was saying before. This guy here looks at the Poincaré disk. So what is the Poincaré disk, if you remember? The Poincaré disk has interesting triangle, right? So I don't know how you say that in English. It's either not. What is the term for this? Au ventre mou. I don't know how you say that. But this is a negative, or at least non-positive curvature property. Okay? And then what happens is that when you have an action of a finite group on such a space, it has always finite point. A finite, yes, not finite, a fixed point. Okay, so there are at least two ways I know to show you have fixed point. One is to show that given finite many points here, there is a smaller disk for that metric which contains all of those, and you take the center. So the center is going to be fixed when you take a Euler orbit. And one other thing, one other way is to show that this kind of space have barycenter. Okay, so you can define barycenter, you know, by minimizing the sum of square, distance square. So there is a way to define barycenter, and of course, when you take the barycenter of an orbit, it is mechanically invariant. Okay, so this thing is called the Bruyatilis fixed point. Okay, so and then I take one x. Yes, but no, you know, when you have a cocycle, it's defined up. The class is defined up to a co-boundary, right? So what I can do is use Soulet, and Soulet tells us that x is g x0, okay, with g in g k prime of t and x0 in this cone. Yes, so what I can do, okay, up to replace z sigma by this g minus 1, z sigma g sigma, okay, by this equivalent characteristic, we can assume we deal with, actually, with x0. Yes, but this x0 comes from this cone, and this cone is fixed. By gamma. And then here comes the shape of the stabilizer. So we know that this cocycle Z sigma for all sigma belongs in what? In G KT prime fixed by X0. But Soule computes those things. And so we know exactly how they are. This is something like that. This is some unipotent part, okay, which depend of X0, but which is a K group. And here you have a reductive group, Li K prime. So I have to say, no, I can erase. So I have to say what is Li. Wait. And so for each I in delta, you know, you have the standard parabolic. Because I had and inside you have a levy. Okay, so my convention is that P is a Bowell, is an ascending convention, and P of delta is G. So, okay, so there are those guys, right? So this is Pi, and Li, this is that. And the important thing is that the Li is in G. Okay, so this guy, this is really the Li, I think, in G. Yes, but these unipotent people here, if you want, by homotopy, but they do not play any role in Galois cohomology. Okay, so by dévissage from you remember the cohomology of GA is always 0. Okay, we have, and actually this was the argument of yesterday. Okay, we have that H1 say K prime over K. So is the same thing that of this guy. Sorry, K prime T fixed by X0. Well, so maybe I take a board. So just to conclude, I just have to write a big diagram and we are done. So the big diagram. And remember, we started from this guy here, K prime over K, or gamma G K prime T. So here was not a cocycle. By changing in, by a co-boundary, we managed to put here in this stabilizer, K prime, T prime, X0. But here, this is H1 of gamma of this LEK prime. And here, I can write the constant class, right? And of course, all these things commute. Okay, so if I go like that or like that, it's the same. Okay? And then my cocycle here, Z sigma, since it comes from here and here, it must be constant. Then we are, it is finished. Okay? It is complete. Okay. So this is what Abramenko and the two rapid chunk, I mean, they have done recently. Okay. Well, I still have some minutes to go further. Okay, so maybe that's if you want to ask a question on that. No? Okay. Well, so I continue with just no proof. It's just to tell you that the story was not over in 1984. So people of Kac-Moody theory were interested not exactly in that, but in the Laurent polynomial case. Okay. So and of course, you know, Laurent polynomials occur. Are important everywhere, okay? So, okay, so this was 6-4. So what about You can say lower polynomial as I'm doing now, k t plus k minus 1. Or you can say also the punctured affine line. Punctured affine line. Okay, and actually here the situation is much, this case is much more complicated. But here is a theorem. So for simplicity, so this is Chernouzov, Pianzola, and myself in 2012. Say k characteristic 0 to make it light. Then, so G over K is reductive. Well, then the map H1 of the Laurent polynomial T plus minus 1 G 2 H1 K T G is bijective. Okay, so you have the same torsors over Laurent polynomials and over Laurent series. Okay, so if you think a bit, it's not okay. Why not? Because in characteristic 0, this ring and this field have exactly the same Galois cover, right? So they have the same absolute Galois group. And let me tell you a bit about the result. So what is not hard is to show surjectivity, okay? But the hard thing is injectivity, and to show injectivity, we need to use actually the Raghunathan-Ramanathan ideas, which we were to take to show that when you have a class here, you can look at its twistors group scheme, okay? And this twistors group scheme, you have to show that it has a maximal torus, okay? And that's the way. And to show that, you involve buildings and this kind of stabilizer, and okay, in a more complicated way, okay? So this is really a building, a Bruyattis building theorem, I will say, okay? And just so you will say, okay, I have this thing I don't know, I relate with this thing I don't know. No, this is not true, because we know a lot here. Because here, first, this is a field, this is Galois cohomology, and for groups which are nice enough, things about, for example, special orthogonal groups and things like that, we know exactly how are quadratic forms over fields like that, okay? So if you take a quadratic form case, it tells you that the quadratic forms are the same over here and over here. So in particular, quadratic forms over such a ring are diagonalizable, okay? Which is not as obvious. So this is a Bruyattis, I will say, tree. Okay, so you have result. We know a lot on this object, and the reason why we know a lot is again Bruyattis theory. Okay. So this is just to complete the techniques of today. So if you go beyond that. You can stay in dimension 1. Much beyond, I will say much beyond. Beyond. In dimension 1. So you have the work of Roman Fedorov, and he constructed, so using affine Grassmannians, he constructed examples but a lot of examples. When H1 RG is not is not H1 RT of G, for G defined over R, and where R is a regular local ring, and we can make even Enselian if you want, okay, which is harder. Okay, so just to tell you that the Raghunathan-Ramanathan theorems, if you cannot replace the field K with by an arbitrary local ring. So of course, I will come that later. There are cases where we have equality. Okay, so the group G cannot be random-wise here. It's kind of special G. So example. So he calls them exotic. It is the title of the paper. So it was 10 years ago, I will say this thing. Okay? Okay, so, but one variable is not everything. You can look also at variation when you add more variables. And here it's even more surprising. So if you go to the problem section, so yes, stuff, examples. So so you can take as base field R, and you can take G to be the unit group of the Hamilton quaternion. Okay, so H, Hamilton quaternion, this is, you know, X is, and Y is 1, minus 1, G is minus 1, and E plus G, EG is plus G, I is 0. Okay, so this is a form of GL2, because H, when you extend H to the complex, it becomes the 2 by 2 complex matrices. And so this group, when you extend to C, G extended to C, this is GL2. And what happened, you can look at H1 R of the G, and so in one variable, we have done it, okay? But you put two variables. And actually, this is the same thing. This thing is much larger than this one, okay? And so in the problem section, we just see not is much larger, just we will see that they do not coincide. And this thing is old, I mean, is due to Oyanguren Sridharan. And of course, there is so this thing actually is 1, because this H1, what does it classify? Like, I mean, we have kind of generalization of Swan-Serre, or what I said with projective modules. That object, that classified invertible right HY modules, okay? And then what happens is that we can construct modules, invertible modules, which are not free, so which give non-trivial classes here. Okay? And so of course, this thing tells you that the Quillen-Suslin theorem does not hold over quaternion. So still you have the Quillen-Suslin theorem, okay? So I explain it like that, okay? H1 of x1 xn GLR. This is trivial. So you have generalization to rings. I mean, this is called Lindel's theorem, okay? And then because I know that I mean, this homotopic machinery needs this kind of vanishing statement. So there are recent work. You have the result of Aravinasok, Owa, and Wendt about generalization of Quillen-Suslin for other groups, and when you plug here a ring R, which is the kind of ring you like, so for example, namely a smooth ring over a field. Okay, and then just to tell you that, I mean, so to have homotopy results, you need assumption of your groups. And what are the assumptions in Quillen-Suslin? In Raghunathan, I forgot to speak about, and Asok and all. So the assumption to make the things, I mean, to behave exactly as we expect are isotropy. Is isotropy conditions. And so GLN is split, is top, but if we have enough anisotropic things, usually it works. And let me end with with also the variant of higher Laurent polynomials, okay, where we have also similar results by Anastasia Stavrova. Okay. Thank you for attention.